Good evening, thank you for joining me for this video. I am Mr. Ish. We have an interesting video here because we are looking at good test questions and they won't be easy. We are looking at 5 of them. 2 of them will be derivatives and 3 of them will be integrals, but in general all of them will not be your ordinary style of questions. This title over here, difficult calculus test, is a bit of a misnomer here. It's difficult if you don't utilize some of the hints I've given you along the way in the previous videos. Otherwise, these questions can be quite easy. So we'll start here with the derivative questions and we'll go to the remaining 3 integral questions. The first derivative question for this test is this provided here. We have actually a derivative provided. It's x cubed root plus x squared cube root, and we have to find the original function. That is, if you had an original function and its derivative was taken, and this is what you ended up with, what was that original function? You have to basically think backwards here, and that thinking backwards would be the hard way of doing it. I will shortly show you the easier way of doing this. Let's look at the hard way. You had to think of an original function such that if you thought about the template for a derivative, and it looks something like this, the power rule, n x to the power of n minus 1, you have to have some sort of similar operation occur over here with this original function such that you ended up with this, and you rewrite this. Let's rewrite our derivative right over here, because this is just a single step over here. We're looking at our derivative as this. This right here is this in exponential format. Everything here is reduced by 1 in terms of the derivative, so everything here has to be added by 1 in terms of your original function. So this becomes a 5 over 2. This becomes over here a 5 over 3. If the derivative has no constants here or no coefficients here, it means it must have cancelled out by that n. What could have been that n? It would have been the reciprocal of this, which would be 2 over 5, and this right here would be 3 over 5. And that right here would be our original function, and it would be the answer. But this was the hard way of doing it. Look at it. Do the derivative template here. 5 over 2 will multiply with 2 over 5. It will cancel out. You'll have this 1. And then 5 over 2 is reduced by 1. You'll end up with 3 over 2. In the second part, 5 over 3 will multiply by 3 over 5. It's reciprocal, and it would cancel out. You'll end up with this 1. 5 over 3 is reduced by 1, and you end up with 2 over 3. And this right here is the answer. But this right here was the hard way of doing it. The easier way is this. You think about the fundamental theorem of calculus, and you take the integral of your derivative to go back to the original function. My derivative is this. You're looking at the integral of the derivative to end up back to the original function. That's what the fundamental theorem of calculus is. The derivative and the integral procedures undo the effect of the other. Let's do it. Rewrite this in exponential format. It's x to the 3 over 2 plus x to the 2 over 3 dx. You're doing the integral of this using the n plus 1 divided by n plus 1 rule, and you'll get to your answer. This will become x to the 5 over 2 over 5 over 2, and this here will become x to the 5 over 3 over 5 over 3. When you simplify this, we're not talking about the constant of integration here, but we're just looking at this. You would get 2 over 5 to the power of x 5 over 2 plus 3 over 5 to the power of x 5 over 3, and this answer is done much more simply without even having to think about reverse thought processes. The second derivative question is a similar format. We have a derivative provided and this additional information. Function with regards to 0 is equal to 5. You have to find what that original function is. That is, you have to work backwards, but we don't have to work backwards because we can think about the fundamental theorem of calculus and just use that. The integral of your derivative will go back to your original function, and that's exactly what we should do. We'll do the integral of our derivative here, 2x minus 3 sine x, and we will do its integration procedure and end up back to our answer, and then this will be utilized shortly. What's the integral of all of this? This is going to be a polynomial one right here. This will become an x squared. This right here will become 3 cosine x, because the integral of sine x, that is its antiderivative, is a minus cosine x. The minus cancels out, you get this, plus c. And this right here represents your original function, which is what we want. But we also want this right here. If you were to plug this 0 in place of this x, you would put zeros in places of all of these x's, and that function over here would then equal 5. That is, you're doing 0 squared plus 3 cosine of this 0 plus c is equal to 5, and this will be your means by which you can calculate the constant of integration. 0 is meaningless. Cosine of 0 is a 1. You have a 3 plus c is equal to 5, and then c is equal to 2. This c right here of value of 2 will fall right in here, and you'll get a better function answer here. Your original function will be x squared plus 3 cosine x plus 2, and this here is your answer. So we will look at 3 relatively difficult integral questions in the rest of this video. This will be our first. We have to find the position of the object if we have a velocity function that's provided and the position at time 0 is equal to 3. If you think back to some of those videos I've presented on the physics or the calculus applications of physics, I've provided a very good recommendation which everyone should technically follow because it makes these type of questions very easy. And you have to think back to that loop I've provided. If you start with a position function, you do its derivative, you end up at the velocity function, and you do the derivative of that, you end up at the acceleration function. And you can go in the reverse direction by doing the integral of each of these steps. The integral of acceleration gives to velocity, the integral of velocity gives rise to the position. And if you're looking at this top loop, the velocity function is equivalent to the first order derivative of the position because you're doing a one single step away from the position function, and the acceleration is a second order position derivative because you're doing 2 steps to get to that, and it's a first order with regards to velocity because you're 1 step away from there. You have to think of all of this in this loop. If you have to find the position of the object and you're given the velocity, you're provided this and you have to find this, then you know you must go backwards using the integral loop. That's why I'm providing you this loop. It tells you in which direction to go based on what you know and where you have to end up. So if you did the integral of this velocity, you know you'll end up back to the position function because you're taking the lower loop. When you do this, what do you get? You'll get a t squared plus cosine t plus c. This will be your position function. But we know this additional piece of information at time 0, this entire function here is equal to 3, and that enables you to solve for this c. And you just have to plug zeros in places of your variable, which is t, and you can easily do it. This zeroes out, this becomes a 1, plus c is equal to 3, and c is equal to 2. So the actual position function becomes t squared plus cosine t plus 2, and that right there is your final answer with the help of this loop we have over here. This next integral question is another application-based question, a calculus perspective of physics, a kinematic style of question, and it won't be hard if you think back to the loop I've already provided in this video now and in several of the previous ones. We have to find the position of this moving object if we're given the acceleration and you know the function is provided. You have position at time 0 is equal to 0 and velocity at time 0 is equal to 2. How do you go about finding the position when you provided the acceleration? Think back to the loop. The acceleration gives rise to the velocity by means of an integral, and velocity gives rise to position by means of its integral, and that's a loop you have to use. You're given the acceleration function, so do its integration procedure and you'll end up at the velocity function. You will do this integration and you'll get a minus cosine t plus 3 sine t plus c, and you know this is going to be your velocity function. But we know the velocity function at time 0 is equal to 2. So you can do a velocity at time 0 and plug zeros in places of these t's and equal it out to 2 and solve for this c. You will have minus cosine of 0 plus 3 sine of 0 plus c is equal to 2. This zeroes out. This is just a minus 1. Take minus 1 on the other side, you solve for c, you get c is equal to 3. So the velocity function all of a sudden becomes this. You have a minus cosine t plus 3 sine t plus 3. Now we're at this step. If you do the integral of this, you'll end up at the position function. That's what we have to do. We'll do the integral of this entire expression here. Minus cosine t plus 3 sine t plus 3 with regards to dt. You'll do this easy integration. The antiderivative I'll put over here will be minus sine t minus 3 cosine t plus 3t plus c. Think back to this, what you have over here. This is your position function at time 0. You put zeros in places of these t's. Minus sine 0 minus 3 cosine 0 plus 3 times that 0. I'm putting the zeros in places of the t's to solve for the c, and I know all of that is equal to 0. This zeros out, this does not zero out. This gives me a minus 3 plus c is equal to 0 and c is equal to 3. I can plug this right in here and complete my answer. The position function for that moving object given the data we had is this: minus sine t minus 3 cosine t plus 3t plus 3. And here is my answer, and it should be good. This will be the last integral question for this video because we're only looking at 5, 2 of which were derivatives and 3 integrals, but this will be a good application. A relatively tricky question, and if you have gone back to some of my previous videos on free fall, this question may not be too hard. We have a drum that's dropped from a chopper 500 meters above the ground. Parachute does not open up. The drum is strong enough to survive a 100 meter per second impact velocity. Will it hold? Meaning, will this drum burst? The parachute did not open, but when it hits the ground, is the drum gonna just burst open or not? That's what we have to find out. What do we know about a falling object? We know gravity is at play, and gravity is also equal to acceleration, which generally is 9.8 meters per second square. These are good physics concepts, but they depend very much on calculus to help you solve them. You don't have to worry about vectors here and say this is minus 9.8. Generally, you're looking at a downward direction, downward facing vector, so you do minus 9.8 meters per second square. But we can eliminate the minus and keep everything positive. If we have an acceleration over here and we did its integral, you'll end up at the velocity, and you do its integral, you'll end up at the position. If we have an acceleration here equal to 9.8 meters per second squared, this indeed is a function, it's a horizontal line. It's just like you saying y is equal to 9.8. If you did its integration, you'll end up at 9.8 t. How do we do that? You're doing an integral of 9.8 dt. You know you're going to bring in the t variable, and you'll have 9.8 t, and you know this is a velocity function, meters per second. If you do the integration of this, you'll end up at the position function, and that's what we need. We're doing the integral of this velocity function, 9.8 t dt, and you know this is polynomial integration. You're going to get 9.8 t squared over 2, which is 4.9 t squared, and this is my position function. Now we have the equation we need to handle this question. Two of the equations we need, because we need this and we also need this. A position function and we need a velocity function. We have a drum that's dropped from a chopper 500 meters above the ground, so you know we can use this. Position at time t is my 500. It's equal to 4.9 t squared. If you calculate the time it takes to hit the ground, that time can then be plugged into the velocity function to determine how that drum will fare when it hits the ground. Let's calculate the time. You solve here for t. You take 4.9 on the other side and you root it. 500 divided by 4.9, and you root that, you get 10.1 seconds. So this drum will take 10.1 seconds in free fall to hit the ground. Now we know that the velocity function is 9.8 t, so velocity at time t, which now is 10.1 seconds, is 9.8 times that 10.1. And that will give me my velocity at the time of impact, because it's taking 10.1 seconds to impact. So velocity at 10.1 seconds will be 10.1 times 9.8, and that will be 98.98 meters per second. What does this tell you? This tells you that the calculated velocity of impact is 98.98, but the drum is able to withstand an impact velocity of 100. Since the calculated velocity of impact is less than the impact threshold for that drum, your drum will hold and it will not burst, because it does not have enough time within these 10.1 seconds and the height. There's not enough time for it to exceed this 100 meters. So the actual impact velocity is less than what the drum is designed to hold. Therefore, the drum should not burst, and your question is done. So that's it for this video. These are 5 challenging, difficult calculus test questions, slightly out of the ordinary, but they should be useful. And I hope you enjoyed this video. Thank you for watching. Have a nice day.